Welcome to the 21st lecture in Physics 10 in 30 lectures. We complete our coverage of electromagnetism with this lecture. In the first section, we introduce Faraday's law by analyzing motion-induced voltage, a situation where a conductor moving in a magnetic field causes a current flow from the magnetic force on the charged particles. Because, according to the laws of electricity and magnetism so far, a physically equivalent version of this event, where the conductor is at rest while the source of the magnetic field moves, because this version doesn't result in a current flowing, we can guess that there is a missing law of electromagnetism. And this law is what we introduce as Faraday's law, which says that changing magnetic field induces voltage. And we discuss a separately named law, Lenz's law, which helps us to figure out the direction of the induced voltage. Lenz's law is essentially the name we give to the minus sign in Faraday's law. And it is a way to conceptually understand the effects of eddy currents, which slow down motion of conductors moving in a magnetic field, or magnets moving near a non-ferromagnetic conductor. In the second half of this lecture set, we demonstrate and explain motors, which also double as generators, with Faraday's law and a way to explain the back EMF limiting the operating speed of motors. We can now fully describe this device that is everywhere in our modern life. This almost wraps up electromagnetism. In the next lecture set, we will look at the collection of Maxwell's equations, that is the full set of laws of electromagnetism, as a way to introduce light, an electromagnetic wave. For now, we start this lecture with Faraday's law. So this is just a coil of wire. It's nothing special. It's just like the other coil of wire. It's only this copper coil. And so you have seen oscilloscope before, and you have some understanding that what the oscilloscope is supposed to show is a voltage as a function of time. X-axis is time, and the voltage is the y-axis. You have seen all of that before, right? And so what it is measuring right now is voltage change across this coil of wire. What do you expect that to be? 0, right? It's a conductor, should be at the same voltage. And when I shake it, it doesn't really change all that much, right? I mean, all of that is as expected. Now, this is what I want to show you, that once you have a magnet in play, then it changes. So, do I need to? I think I need to put the right amount of exposure where you can see both the coil and the signal on the oscilloscope. So what I'm going to do is I'm going to put this magnet on some ground somewhere. So, even though you can't see it, you can kind of visualize that there's a magnetic field coming out of this, like a very strong dipole magnetic field. And when I move this within the magnetic field, something interesting happens with that electric signal. So when I drop it, it went down, right? And when I pull it out, then the voltage goes up. And it's directional. So if I change these two connections around, then this time when I push it down, then the voltage will go up. When I push it down, the voltage goes up. When I pull it out, the voltage goes down. So, okay, where is that coming from? So this is what your textbook calls motional EMF. And I've been trying to get rid of that word EMF. So what I'm trying this semester is motion-induced voltage. Yeah? So this is interesting, but ultimately, I didn't teach you anything new. It's just the application of something that you already knew. Right? And I promise that we can use this
to figure out that there's a missing law of electromagnetism. So let me show you a slightly different version of this effect. So the slightly different version looks like this. The coil is sitting there, it's not moving. And what I'm going to do is, instead of moving the coil, I'm going to move the magnet. So let me put it on a stick so that it's easier to move. I'm going to stick the magnet either in or out. So you see voltage there, right? Now, would you have expected to see that voltage? Yeah, kinda. You could have expected it. If you, how many here are familiar with the principle of relativity? Kinda, when things, it's the relative motion that matters, not absolute motion. So the question of when you look at these two approaching each other, question of which is stationary. That's an academic question. That's a question without a physical meaning, because in the reference frame of this magnet, it's the coil that's moving. That's what you saw before. But imagine you are the observer on the coil, then it's the magnet that's moving. So considering the principle of relativity, you could have theoretically expected the effect that you are seeing experimentally there now. When you have this magnet that's moving, that generates voltage. But the coil itself isn't moving. Now, this is what I want you to look at. Look at all the laws of physics that you know. So this time, there's no wire that has any kind of velocity. Here, velocity is 0. The only thing that has velocity is the magnet, but I'm not really looking at the force on the magnet. I'm looking at the force on the things inside the wire. So velocity is 0 for whatever it is you are looking at. And you want to get something that's close to motional EMF. So as you look at this, is there anything here that says if you have a changing magnet? So, when I move this up and down, this is what it does. It changes the magnetic field. So when I move this magnet around, this is what I'm doing. Closer to the magnet, magnetic field is stronger. Farther from the magnet, magnetic field is weaker. So as I move the magnet up and down, I'm changing the strength of magnetic field at the location of this coil. Right? So the question comes down to, is there anything in our law of physics that says when the magnetic field changes, there must be voltage? Right now there isn't, right? But so this is where you have to assume that something like Faraday's law exists. Because other than the fact that you see an experiment, you also can reason it through. That you consider this picture, stationary magnet and moving coil, and that has to be physically equivalent to stationary coil and moving magnet. And when you take the laws of electromagnetism as it's written here, those two are not, they are not symmetric. So when you look at moving coil, something interesting should happen. But when you look at moving magnet, well, nothing interesting should happen when your physical intuition says that both of those are the same physical picture. In fact, if you want to make it symmetric, they can be moving towards each other. Yeah? So this is the Faraday's law, which resolves this paradox, which makes laws of electricity and magnetism consistent with what we expect and what we see in experiment. So let me write down Faraday's law. It says, it actually looks quite similar to Ampere's law, which kind of makes sense because it's a law that relates to the voltage. So this is what Faraday's law says. The line integral of electric field, E dot dl, and this line integral is around the closed loop. So when you do a line integral around the closed loop, so do you guys remember what kind of geometric object a closed loop also define? Like if you have a closed loop, all right, great, you have a closed loop, but you have one other geometric object from this. Surface that's enclosed by this loop, right? So once you have a surface, then you can define a flux, right? So that's how we did it for electric flux here. So we can do the same thing for magnetic field. So with this loop that we have for, call it Faraday's loop, I think we still call it Ampere, whatever. With this closed loop, you can define a surface. So you can look at magnetic field going through the surface and calculate the magnetic flux. So, so let me just write down that definition of magnetic flux. So the magnetic flux, we use this symbol, capital Phi, subscript B. All this means is it's the surface integral of B dot dA over some surface. It doesn't have to be closed, it can be open. If it's a closed surface, then it's like the Gaussian surface that we are using. If it's open surface, then it's like the open surface that's bounded by this loop. Yeah. So what Faraday's law says is that there's a relationship between this line integral of electric field and this magnetic flux coming from the magnetic field. And it's not just, it's a different type of relationship than what you have seen before. So, so right now there's a magnetic flux going through the loops of this wire. But you don't see any voltage there, right? You only see the voltage when the magnetic flux changes. So here, this voltage is going to be related to magnetic flux this way, minus the rate of change of the magnetic flux. Yeah? So there's a time derivative here. So far, in specifying all of this, there wasn't really time derivative. I guess you could have put in some time derivative with the current, but we didn't. So this is Faraday's law. So I guess I made the box too big. So this is Faraday's law. This is what makes this picture consistent, that whether the magnet is the one doing the moving or the coil is the one doing the moving, the effect of either happening is the same. Yeah? So this is the magnitude of induced voltage that Faraday's law gives you. Compared to this, oh, it's the same voltage. Same magnitude anyway. Good. Now, let me wrap up the introduction of Faraday's law with this. So because I have good memory, you will always find me always writing down this minus sign. That's part of the Faraday's law. You forget it, you did something wrong. It's like forgetting this minus sign here. It's one of those serious sign errors. And, but the thing is, it's hard to really know intuitively what the effect or the consequence of this minus sign is. That's why we give this minus sign its own name. In your textbook, that minus sign is called Lenz's law. And we have a whole description of consequence of Lenz's law. But what I want to tell you now is that, when you hear Lenz's law, it's not a separate law. It is a part of Faraday's law, but it's this one particular, somewhat abstract part of Faraday's law that we are giving you this word description for, so that you can apply it. When you do this correctly, you can be sure that you got the directions correctly, and you can kind of forget about this minus sign. But per division level work, this minus sign will naturally give you the same result that Lenz's law is giving you. So let me describe Lenz's law, because it's a way to try to get at this thing that's harder to figure out just purely mathematically, because it's too abstract. It comes down to this. So when we use the motional voltage, induced voltage, the result we got is that the current that you would induce, that the current goes clockwise, right? Yes, that's what you got. So it might feel like you got more out of this motion-induced voltage business than you got out of Faraday's law. Because with Faraday's law, put my hand up. I don't know anything about direction. I'm just gonna try to calculate the magnitude. And what I'm telling you is that Faraday's law also gives you the direction. And the direction given by Faraday's law will agree with the direction given by motional voltage, motion-induced voltage. So let me, I guess, write down Lenz's law. It's a bit complicated law. So let me try to state Lenz's law here. Lenz's law. Let's see. So it's related to Faraday's law, where change in magnetic flux induces the voltage, right? And this voltage is going to induce current if it's conducting path, right? All of that is reasonable so far? Okay, so Lenz's law deals with the current. It says that the direction of induced current, that is, the current that you would get from the voltage in Faraday's law, it says direction of induced current opposes the change of magnetic flux that induced it. Does the meaning of this clear enough? It's a bit of a complicated sentence. So let me illustrate what I mean here. So here, as this boundary moves to left, when you look at the direction of change of magnetic flux, what direction would you say magnetic flux is changing? Like if you treat magnetic flux like a vector-like quantity. Coming out of the board more, right? Okay. So that's the change in magnetic flux. What Lenz's law tells you is that the induced voltage around this loop, it's going to generate a current. And the current must be generated in such a way that this change is being opposed, meaning the magnetic field due to this loop of current should point into the board. That's going to be opposing this change here, right? So what direction of current should it be? Clockwise or counterclockwise, so that the magnetic field due to induced current opposes this that's coming out of the board. Clockwise, right? So this is a shortcut rule. Clockwise loop of current, magnetic field points into the board. That's the same direction we got with the motional voltage. Yeah, and actually, this Lenz's law, it makes a physical sense. In fact, if it was the other way, you would get a really absurd result. Let me show you why. So let's go back to the initial picture for motional voltage. So this clockwise current, it was set up by this loop that's moving to the right, right? Now, I want you guys to think of the force on this loop, not because of this velocity, but because of this current I that's flowing in this loop, clockwise direction. So what direction is the force on this loop due to this current? Well, I is downward. So this is where you have to use the modified version of the magnetic force. As in, magnetic force on wire is equal to I L cross B, right? So, direction of current, cross B. So direction of current, cross B. What direction is the force? To the left, right? So because of this current here, there is going to be, how do I draw this? Sorry, this is getting very cluttered. Because of that current, there's going to be a leftward magnetic force. What does that do to this initial velocity that it had? Yeah, it's going to decrease, right? It's going to slow down. So this is what you would see physically. And if I could actually set it up, if this is a region of strong magnetic field, and I throw it in here, as it goes through, it's going to slow down. Because as it tries to pass through, there will be a current generated here, and direction of current will be such a way that the I cross B will oppose the direction it's already moving. So it'll slow down, come to a stop, and stop. Now, I want you to imagine, what if this was a plus sign? What if Lenz's law was the exact opposite? That the direction of induced current not opposes, but like strengthens the change of magnetic flux that induced it. Like what will happen as this moves into the magnetic field? It'll speed up, so when something moves here, it'll like get launched away. And like your intuition says that if something slows down to stop, you can understand it, right? Mechanical energy went into some thermal energy. In fact, if you have a current flowing, it has resistance, you're going to get Joule heating. So it makes sense that you're going to lose mechanical energy. The other picture is just an absurdity, where like if it just takes off, like where is that energy coming from? And this is the way that you can understand something called eddy current. So let me actually pass this around. Oh, I don't have, well. So I'm going to pass it around. Because there's not enough time per person, I just want you to flip it up and down to see how it behaves as it's, I need one of these.
So that cutout is there so that you can see through the side of the copper tube, and you can see from this end point view that there's nothing special in there. It's a copper tube. It's a tube made of conducting material, the conducting part being important. I'm going to support it vertically, and all the stand stuff, they are I think made of aluminum. They are not ferromagnetic. That's the important. So these are the two slugs. This is one of them that looks like that, and this is the other slug. Also looks metallic. Now, when I drop that, nothing surprising. And let's look at this other slug. So it's sliding down very slowly. And this is the result of Faraday's law and Lenz's law. So what's happening as this slug is sliding down is you have to imagine this slug as a kind of a bar magnet, but maybe a very strong bar magnet. So I forget which end is North Pole, which end is South Pole. For the purpose of illustration, it doesn't matter. Let's say it's North Pole at one end and South Pole at the other end. So that this permanent magnet generates a magnetic field that looks maybe something like this. So as this magnet is sliding down, you have magnetic flux through different, you can imagine different loops. I guess for one purpose, you can imagine loops that go around the tube, except in this particular tube, that loop is interrupted. But if you imagine the sides were closed, then that's the easiest loop to imagine. So if you imagine loops like this, then as this magnet falls down, the magnetic flux through this loop is changing. So so you have magnetic flux that's poking upward, and it's as this magnet slides down and moves away, it's decreasing in strength. So the change in flux is happening in the downward direction. This would be the change in magnetic flux. And Faraday's law says that if there's an electric, the line integral of electric field or voltage, that there's a voltage associated with the rate of change of magnetic flux. So there's a voltage induced around this loop. And Lenz's law, which is referring to this minus sign here, says that there's you can figure out the direction of the electric field this way. That if you imagine the current being produced by this voltage, induced voltage, then the direction of current is such that it opposes the direction of the original change in magnetic flux. So here, let me use one of my shortcut right-hand rules. So I want the induced magnetic flux to point upward. So I would want, as viewed from top, I would want my current to flow counterclockwise. So I want my current to flow maybe in this direction, counterclockwise. From this side, it'll be going kind of into the plane. Here, it's coming out of the plane. Now, if you imagine a current loop that's going like that, then looking at that, you would say, oh, so current loop going that way, it's going to generate magnetic field that looks like this. These will be the magnetic fields produced by the induced current. And and as you look at its induced current or the magnetic field due to the induced current, if these magnetic fields remind you of magnetic field of a magnet with the north pole at one end and south pole at the other end, then that should remind you of that. That's what they look like. And in mechanical terms, this is what's happening. This south pole end is attracting this north pole end, slowing down the falling magnet. And you can do this kind of analysis consideration for any loops within the conductor that's surrounding this moving magnet. And what you'll find is that direction of this magnet will always be oriented in such a way that it opposes the motion of the magnet, the permanent magnet that's causing the original change in magnetic flux. So if you did an analysis like what I'm doing up here, analysis for this loop will show that, oh, it's not north and south, it's south and north, so that the south pole is repelling the south pole and again slowing it down. And it happens for basically all the geometries that involves moving magnet near a conducting material. So that's why we give it a special name, because it's not the specific geometry that's important, it's the effect. Effect is that it produces eddy current. We call it eddy current because if you visualize the currents within the body of that conducting material, it looks like the water flowing, water eddies. And directions of those eddy currents are always such that it mechanically slows down the magnet. So that's what this demonstration is showing. And that's so with these induced currents, the magnet is being slowed down, which is why you are seeing it takes so long to slide down that relatively short section of the copper tube. I think I had a couple more demonstrations with this video. Let me just play through. Oh, I think I want you to slide both of them down together. One of them is a ferromagnetic, so they do stick together. But it's overall heavier, so it falls down faster. And I think I want you to give you a little bit of a closer up, so that will be the next segment, and then we'll move on. Just the magnet, not the ferromagnetic slot, just magnet. So slow I can just move it up to accommodate falling.
So yeah, so that's the eddy current demo. If you wanna play with this, you can. And in the lab today, what we are going to look at is an electric motor. And technically, actually, we could have introduced the electric motor much earlier because it's based on this magnetic force. But there's a reason we delayed it until now to introduce electric motor. Because to fully understand it, you actually do need the Faraday's law. So, you'll look at that in the lab. Yeah, I think I covered it, for your lab. So, any questions, comments? What I want to show now is it's kind of an electric motor. You can look at it that way. This can operate as an electric motor, and I guess I will show it working that way in a few minutes. But this is sold as
it's sold as a generator. So let me first show it to you working as a generator. Let's see, how did I want to do this? I think what I need to do first is I need to stop sharing my screen so that the video is relatively the big thing, and so that I can also look at my own video. And I'm going to be switching my camera at some point so that I can change the angle and show you some of the demos that it's easier to place on the desk. So I guess what I want you to see is that the construction of device is really simple. Let me switch the camera now, actually. I think the external camera that I normally use, it doesn't autofocus. I disabled it, and it doesn't work well when I have the device I want to move back and forth. So this is the device, whole thing. It's connected to some wire stuff at the end, but it's a fairly simple thing. And if you have seen any electric motors, what you see at the end here might look similar to electric motor, as in this thing in the middle, that's the shaft of the motor, and you can't see inside the construction, but if this looks familiar to you like an electric motor that you might have seen elsewhere, well, it is an electric motor. It's got these wires connected at the end here to the two terminals. That's the wires that are connected here. And so why am I calling this a motor? Isn't this a generator? Well, it is a generator. It's not a generator. So let me show it to you working as a generator. Let's see here. Gonna bend. Okay, I think I need to put this way out here. Okay, so I have these light bulbs. Wait. Yeah, let me connect this generator to, so the leads of the generator to the two ends of the light bulb. And I'm going to make sure, this has two output modes, one low output, high output. I'm going to make sure that I put it on the high output mode. Why am I connecting this? I'm going to connect it closer because it's easier to connect it that way. Sorry, slippery. Wow, this is so slippery. Maybe it's because I'm using my left hand. It's like trying to use chopstick with your left hand. Okay, so I have the leads connected here, and I have this thing that's sold as a generator. So let me turn it, and yeah, it's a generator. Yeah, it's on. Yeah, it's on high output. So on high output, and on low output it works as generator too, but it kind of limits the current. So yeah. So anyways, high output. Yeah, it's a generator. So then why does it look like a motor? It's because it's also a motor. So that's why I have two of these, so that I can show it to you, working as a motor and a generator. So I have two of these now. I guess I'll leave the camera angle here so that you can see both of them reasonably well. So the one on the left, they are here. And I'm just going to connect the two of them so that one of them can work as a generator and the other can work as a motor. So I'm gonna, I guess the direction doesn't matter too much. It just will change in what direction these things turn. But let me just, for visual, I don't know, satisfaction, I'll just have the same colors, black wire to the black, red wire to red. But they can be up the other way around. It doesn't have to be the same. And let me make sure they are both on the high output mode. This is on high output, and this already was. So I'm gonna let me take the thing that I was before using as generator, and I'm gonna turn it. And as I turn it, this is what happens. So this is what I mean by saying that this is also a motor. So when I turn this, this works as a generator using Faraday's law to generate current here because there's an induced voltage. That voltage drives the current. And when the current goes into this motor, then that motor, there's a torque on the current carrying wire in there. And that torque turns this thing in the shaft. And there's a whole set of gears that turns the crank. So when I turn this, the thing here turns. Now I can reverse it. And by the way, you can kind of see that these two are not connected one to one. When I turn this fast, you see it turning, but watch when I turn this very slowly. When I turn this very slowly, making sure, I'm not generating so much current that it can't, so it's not a one-to-one relationship. It's a mechanical energy to current to mechanical thing, and there's enough losses there that if I do this slowly enough, that I can turn this without that other thing turning. But if I do it fast, then it turns. Now, let me put down my generator so that it can now be motor, and turn this motor so that it can be generated. So yeah, it's and I think your textbook doesn't give it enough emphasis. Every motor is a generator, and every generator is a motor. That's just how it works by the physical principle under which motors and generators work. That it's like there's no way for there's no way for a motor to also not be a generator if you reverse the direction in which where the mechanical energy is input versus where it's coming out. Every motor has to work in some sense, or it should be capable of working as a generator. And I don't know, I guess I'm not 100% sure if it's, I mean, you can always, break it. You can put in ratchets and whatnot. You can make it so that it can go the other way. But unless you take effort to disable it somehow, every motor by default can function as a generator. Two-part lab. One part deals with, or I guess it's got two different sets of equipment. One of them works with what's called world's simplest motor. That's the kit provider's name. I think if you just Google search world's simplest motor, you'll find that. It's this. I mean, I guess they in the instruction they had the people using battery body to have this coil of wire. That's what's important. And with the coil of wire, with the ends stripped a little bit, you can have this arrangement. This is the magnet placed here. This coil of wire hanging over a magnet, connected in such a way that it'll be connected to a battery. It turns like a motor. So it's a motor, and it's the world's simplest motor because it is the fewest part you can imagine. So this is the lab working with these two simplest possible arrangements that illustrates magnetic force on a current carrying wire. And if that's the only thing, one might ask, so why didn't we do this earlier? We were covering magnetic force like 3 weeks ago. So we could have done this earlier. Why now? Why now is we needed the Faraday's law to describe some of the restrictions on the operation of a motor. So that's why we are, yeah. And I think one of the questions get at that. Yeah, something like the two different questions. One about the measure the frequency of rotation, and question of what parameter limits how quickly the motor can turn. And in the lab, as you're doing the experiment, you would find that it's the voltage that that determines the turning speed of the motor. If you increase the voltage somehow, then it will turn faster. If you decrease the voltage, it turns slower. And the and that connection can be explained the best using Faraday's law. And the other question gets at that when you are looking at this arrangement, with a battery in here, a wire connecting one end to the other end of the battery, it'll look like we have shorted the two ends of the battery. In fact, the homopolar motor, yeah, we are shorting the top to the bottom. And if you remember when we were doing circuits, that's the one thing I tell people not to do. It's a safety hazard. And so this question is getting at why is that not a safety hazard when you do it with a motor? And the reason is Faraday's law, induced voltage. And in fact, the thing to be careful with when you're working with a motor is that if you somehow brought the motor to a stop, apply a torque so that prevent it from turning, that's actually dangerous for the motor. Because at that point, you no longer have induced voltage that's opposing the voltage of the power supply, and you might have a situation where too much current flows through the wire and causes other damage to the motor. So yeah, as long as the motor is running, it's safe. The current output is limited, and yeah. So let me start out with the demonstration of these two setups. You've heard me describe them now, but video is a lot better than my words. So let me just show you the operation of the motor. Okay, let me change my share setting. So this is the world's simplest motor. I wanted to show you the individual parts. This is the plastic holder that holds everything. There are the electrodes that go on the two ends to connect the battery to the wire. Yeah, I fiddle with it for a bit to figure out which way it goes. And that's the battery. It's used for two different, as a cylinder reference and as a power source. But anyways, I'm gonna and the magnet. I'm gonna put this away. I already assembled it because I want it to be short. And what am I doing? Oh, I want you to show the electrodes for some reason. Okay, that's the coil of wire. So it's enamel coated, so it's insulated between each loop. Now, at the end, if you look at it carefully, you'll see a little bit of a sheen. That's where the enamel has been stripped off. Now, it might look like it hasn't been stripped off uniformly, and that is on purpose. If it's stripped off perfectly uniformly, then the motor shouldn't work technically because basically the net torque over a whole rotation adds up to zero. Now, in experiment, it turns out not to really work out that way. Even if you strip it all the way around, it still works. I imagine because the electrical connection we make is such a poor connection that as the thing turns, there's enough asymmetry that it still works. But anyways, the kind of instruction is to strip one side, and you want to kind of figure out when the stripped side is in contact that there's a torque on the wire. So that's what I'm showing in the video, the stripped portions of the wire where electrical contact will be made. You might say moving a little bit funny. Sometimes you need to give it a little kickstart so that it's not stuck in a dead zone. Yeah, there it is. World's simplest motor. And it'll basically run in that configuration indefinitely until the battery runs out. It could run for quite a few number of minutes or I don't know how long. Yeah. So, and so here I'm trying to do something to demonstrate something, but I don't think it really worked. I want you to measure the voltage at the two ends to illustrate how the voltage of the battery measured while the motor is running is different from voltage measured when it is not. In fact, that's how people measure the frequency of that rotation with the oscilloscope, not digital multimeter. But this didn't really work out because let me just skip ahead. Because when I remove it and do it without the wire, it's so I think it's just a bad contact. So anyways, let me just skip this portion. It didn't end up demonstrating what I wanted to demonstrate. And yeah, and I'm just trying to get the motor running again. In the future, I'll probably resplice this video so that I can just. But this is world's simplest motor. That's all the parts there is. I think you can buy the kit for like $5 or $10, pretty cheap. Um, and you could swap out this magnet here for a better magnet. I've tried it with a stronger neodymium magnet. Didn't work out all that much better. I think maybe because well, it didn't work out that much better. I think ideally you want uniform magnetic field over the entire region. And when I describe um, the working parts of the motor in a little bit, um, I'll be assuming basically the whole current carrying coil is in a uniform magnetic field, which is not the experimental setup, but big huge magnets are expensive, so. Um, and this kit is a very cheap kit. That's what it comes down to. So this is a working model of a motor, and you saw it work, and it's a model. In that, it's not. It doesn't have a practical, useful motor would have more parts. It'll have more magnets spaced out and coil spaced out in such a way to smooth out in how often the current carrying loop will feel the magnetic force. So that's what practical motors would look like. This model of a motor is much more simplified, so that it's easier for us to see the working components of this motor. So let me make this smaller because I want to grab. Let me grab just one other screenshot because there are basically two orientation of this loop that's worth considering as we look at the operation of this motor. So these two snapshots are illustrating two orientations of the current carrying coil. Let me talk through the operation of this model of a motor. And I guess for the purpose of this illustration, I'm going to assume that the top of the magnet is north end. I don't know if it is. It might not be, but I'll just assume that it's a north end, so that I have some way to draw a magnetic field in a way that makes sense in some way. And even though in the real physical picture, I have only this tiny small magnet. So my actual magnetic field looks more like this kind of a dipole magnet. That's what my real magnetic field looks like. But for the purpose of discussion, let me say that let's just suppose that we have a region of uniform-ish magnetic field that over the entire current carrying coil. It uh, Again, this is not quite realistic. It's not, or that's not how the actual physical demo is set up. But for the purpose of talking about what's happening with a motor, all we need is a uniform magnetic field. We don't need that it be a dipole field or that it has some spatially varying component. Nothing like that is necessary. So I'll just describe a uniform magnetic field, the simplest setup that we need for this motor to work. So, um, so in the simplest illustration, we can model the current as a single loop of current. So the way the actual physical demo is built, it has multiple loops, but that's so that there's a greater magnetic force. We're going to be talking mostly about direction, so we can just to say, I think this is the positive end. Oh wait, I want to be careful with the direction. Let me do this. I'm just gonna draw a direction of current, and if it turns out that I messed up, assuming that this end is north, I'll just reverse it. So, um, so looking at here, I have, let's say, current coming in from here, and let's just say current is flowing this way, and it makes some loop, and then eventually goes out this way. So that's the direction of current. And let's assume some similar direction here. Current comes in, And I'm gonna say on this end, it's going into the page. So goes around, 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 and here it comes out of page and then goes this way. Okay. So the direction of current here would be flowing that way, this way, and the far side is flowing that way, near side is flowing this way. Okay. So that's the arrangement for this motor. And what a motor is a torque exerted on a current carrying wire by magnetic field. That's really all that's necessary for the operation of motor. So, so we can quickly analyze what kind of torque is exerted on this current carrying loop by this magnetic field. Let me draw copy an illustration of that here. So I have a coil. I'm gonna imagine a more rectangular kind of coil with a segment that's going into the page and a far segment that's flowing left to right, a near segment that's flowing out of the page, and then or the segment that's coming towards us or towards us, and a segment that's going from right to left. And then the loop goes however many times, and then current eventually goes up. So this is one current carrying loop. That's a version that's there. So when we have magnetic field in the region, so we can do the right hand rule to figure out the direction of force on each of the segments of this wire. So let's do that. So the first segment I'll consider is where current is flowing into the screen, into the page. And I want you so that magnetic L cross, so I'm using this expression that you have seen before, that magnetic force on a current carrying wire is current times L cross B. So the direction of L is into the screen, and I want my hand to be oriented so that when I curl my fingers, they can curl, up towards the magnetic field. So my force is rightward for this segment of wire. So I have a rightward force here. Okay, let me just double check from my perspective. Okay, and the segment that's farther away from us with the current flowing from left to right. So left to right, cross B. So left, no, that's right to left. Left to right, cross B. Okay, so there are magnetic forces coming out of the page. So let me just do that and just double check that you're good. And here with the L coming out of the screen, L cross B. Okay, so the force is to the left. That's the direction. I think I can kind of guess this one. It's probably gonna be this. Let's just double check. Current is flowing from right to left, cross B, and yeah, magnetic force is pointing into the screen. Okay, so those are the direction of the force, and as you look at that, horizontally lying loop, if you are figuring, it looks like I'll have that net torque is 0, then you'll be right. These forces around this center of rotation, these forces have no lever arm. These two forces were never going to cause any torque. And these two forces, if this loop is horizontal, then the lever arm for these two forces are 0. They're just stretching the loop out this way. Stretching? No, they are compressing. They're just compressing the loop in this way, but they are not causing it to rotate. So this is one of the things to watch out with a motor. A motor of this kind of design has dead zones. There are orientations of the current carrying coil that won't produce any torque. And now with the more practical motors, there are things that people do so that motor won't get stuck in a dead zone. But with the world's simplest motor, yeah, that can happen. Can get stuck in a dead zone. So let's analyze the other orientation to see what it does. So for the other orientation, we have current coming in, and on the left side of the coil will have current that's flowing upward, I think, yeah, upward. And then on the top segment of the wire, current flowing to the right. And I know it's a circle. I'm just going to draw it as square so that I can talk about the four sides with the four orientations. And the current flows down here, and then current flows right to left to here. And then after some number of loops, it leaves. Okay, so let's do the same analysis. We are figuring, okay, magnetic force is IL cross B. So and I'm figuring the direction of the force on each segment of wire, or each kind of orientation of wire on this circular thing. So for IL cross B, for the left segment, I have, so my current is flowing upward, and I want to bend my fingers in such a way that it can bend towards magnetic field, and I see that I can't do that. Magnetic field is also pointing upward. So around here, on this segment, magnetic force will be zero in this orientation. Okay, let's keep going. At the top, where the current flows from left to right, so I want it so that IL cross B, okay, magnetic force is pointing out of the screen. Let me just make sure that looks correct from my perspective. Okay. On the right segment, I think the same thing is going to happen, because for this segment, the magnetic field is anti-parallel, and 180 degrees sine of that is also zero. So magnetic force here is zero as well. Okay. At the bottom, I have current flowing from right to left, and magnetic field. So this is IL cross B. Thumb is pointing into the screen. So magnetic forces into the screen there. Yeah. Okay, so these two look promising because they do now have lever arm. This is lever arm, and this is lever arm. So if you imagine this, these two combined forces will tend to rotate this whole thing in kind of this way. So if you imagine looking at this coil from a point of the observer who's over here, then from this observer, it'll look like it's spinning counterclockwise, I think. Yeah, so there, from this observer's perspective, net torque is counterclockwise. So that's the torque on the loop of wire. So applied over some amount of time that'll cause the loop to rotate. And that's exactly what you see with this world's simplest motor. Now, I don't remember in the demo if it actually spun in this direction or not. If it actually went the other way, what it would mean is one or the other, which is it could be that the current was actually flowing the other way. I don't know. I couldn't track the direction of wire in this screenshot. Or it could mean that the direction of magnet is opposite. Flipping either of them will flip the direction with which motor runs. And practically how this demo works, the direction in which it spins, it would also depend. Wait, would it depend on? It does depend on which side of this straight wire is stripped, because I'm supposed to strip only one side. So when the whole loop is in one orientation versus the other, so in one orientation, you can imagine it here. If I imagine flipping this around so that after it has turned 180 degrees around, then the current at the bottom is now flowing left to right, and the current at the top is flowing right to left, then you can see that the direction of torque will flip. That's why you need a bit of an asymmetry. In a practical motor, they have something called, either it's called the alternator or commutator, something that will flip the direction of current as the motor turns so that the net torque is in a consistent direction. For our world's simplest motor, all we have done is introduce a bit of asymmetry so that in one orientation there will be torque, And in other orientation, there won't be torque, but the kind of the inertia will carry through, and the motor will, as long as the motor receives enough integrated torque over a full turn, it will continue to run, as you've seen in the demo. So that's the motor. Now, so far, so as you are hearing this description, if you are asking yourself the question, so why didn't we do this earlier? Well, yeah, you're right. We could have done this earlier. And here is why we are now talking about motor. Because if we had talked about motor before this week, then there's one aspect that we couldn't fully explain, which is this. So as you imagine this setup, as you imagine this net torque that's being exerted on the coil of wire, you might see that so you have this torque whenever the wire is in this orientation, and there's nothing that says as this thing spins faster and faster, torque should be less. And if you, just as if you have a constant acceleration for an unlimited amount of time, you'll have a very, very high velocity. You could ask the same question if you have a constant-ish torque, which would lead to constant-ish angular acceleration in the counterclockwise direction for an unlimited amount of time. One could easily ask the question, why doesn't this motor speed up kind of without limit? Why doesn't this motor spin really, really fast? And and you might say, oh, eventually, the friction and whatnot is going to be too much. Okay, then why not the regular motors with the frictionless, friction minimize the bearings and all that? Why don't those spin out of control? And I guess with the more complicated motors, you could imagine that there's some kind of regulator built in. Well, they don't, but what they do have is nature's regulator. There's a secondary effect that will happen as this loop of wire spins. That's going to naturally limit how quickly this can spin. Imagine this loop spinning back and forth between these two orientations. I mean, it's not quite back and forth. It's turning 90 degrees each time. As it's doing that, something is changing with the loop. So with the loop in this orientation, the magnetic flux here is zero, because you can kind of see none of the magnetic fields are going through the loop. When the loop is in this orientation, the magnetic flux, well, it's not zero. Its magnitude is the area of the loop times the magnetic field. So as this loop spins, you have a change of magnetic flux. And as you learned this week, the change of magnetic flux, or the time derivative of magnetic flux, is associated with this line integral of electric field, which is, I could give this another name. A line integral of electric field is voltage. So this rotation of the loop itself induces a voltage in this coil of wire. And this voltage is always induced in such a way that it opposes this change in magnetic flux. So this is what your textbook calls back EMF. I'm trying not to use the word EMF, so let me call it, what was I trying to call it? I tried calling it back voltage for a while and it didn't sound right. Am I calling it reaction voltage? Not really. I don't know. I should just call it back EMF. That's the terminology your textbook uses. There's an induced voltage in this coil that's going to oppose the voltage that you are applying. So there comes some equilibrium speed where the applied voltage equals the induced voltage that's opposing that applied voltage. And at that point, the whole thing is not going to really draw all that much current. So So if you imagine a frictionless, perfect coil of wire, a perfect motor that's spinning frictionlessly, then there's a kind of an equilibrium speed where the coil won't be drawing any current because the voltage you are applying is precisely opposed by the back EMF. Or in the case of a more realistic motor, the only amount of power that's needed to be drawn is the same power that's needed for the motor to do mechanical work, either against the friction or against the load that you are imposing. So this portion of this part of the operation of motor is important because uh, this makes it so that a free running motor is safe. It has some natural maximum speed that it'll run to that depends on the magnetic field and applied voltage. So the applied voltage acts as a natural regulator. It limits how fast the motor can spin. And at the same time, if you want the motor to spin faster, okay, apply a higher voltage, and then it'll be able to spin faster. And this is again why it's dangerous to just stop the motor, because if you just stop the motor, then nothing no longer the amount of current that can flow through the coils is no longer limited by something other than resistance of the wire. And if you just want a very low resistance wire connecting one end of battery to the other, that's a short. It can draw a lot of current, and that's dangerous. So simply stopping the motor cold is it's not something that you should do. So while the motor is running, it's perfectly safe because this induced voltage will oppose the applied voltage, limiting how fast it can spin and how much current it eventually draws. So okay, so that's the lecture on electric motor that we really had to hold off until now so that we can discuss the full detail of everything that goes into operation of motor.